I'd like to introduce our next presenter, and that is Philip Hooker, VP of Strategic Programs and Cloud Innovation at Software AG. Phil's got 25 years of experience working with companies like Orange, Nokia, Barclays, and Wipro on strategic business development and transformation initiatives. Today, he leads programs to accelerate the exploitation of cloud, and Phil is an original with Cumulocity. Philip, welcome.
Excellent. Thanks, Keith. So industrial equipment manufacturers are facing the same challenges when creating connected products. How do you create a secure product that is still easy to manage? How do you create and operate a product that remains reliable and robust 10 years into the future? And how do you do all this whilst balancing features versus cost? These product manufacturers need three simple things: secure cloud and hardware agnostic connectivity, robust device management and monitoring, and this software to be efficient on resource-constrained devices. My name is Philip Hooker, VP of Strategic Programs at Software AG. I'd like to show you how the open source ThinEdge.io initiative can change your connected product strategy. As mentioned before, IoT connectivity is transforming the industrial equipment market. The requirement to have increasingly sophisticated analytics close to the data source is driving pioneering PLC manufacturers like Brainboxes and Kunbus to embed standardized compute modules into their devices. This allows industrial automation service providers to rapidly prototype solutions and deploy them straight into industrialized devices, minimizing downtime, speeding response time, and maximizing profits. IFM's IoT provides a way to easily monitor, manage, and analyze data online. With IoT, the readings from over 10,000 sensors from more than 200 manufacturers are visible in the cloud in less than 1 minute. The solution consists of an IoT cellular gateway, cloud app, and a European-wide flat data rate. Another example is Gardner Denver's Icon solution, which provides air compressor customers with proactive real-time insight that ensures machine uptime and efficient performance. Icon is available as standard on all new machines and can be retrofitted to existing compressor installations. It even supports auxiliary equipment and non-Gardner Denver-based products, providing customers with a unified digital experience to manage their entire compressed air system. Addressing the connectivity challenge is not made easier by the lack of standardization across the industry, forcing enterprises to make early decisions that have potentially irreversible consequences. Until recently, manufacturers had limited choices. Some enterprises chose to make sense of the jumbled technology landscape and develop the connectivity adapters for their solutions themselves. This is a considerable undertaking and shouldn't be underestimated, especially as embedded IoT software engineers are a scarce and expensive resource. IoTera estimates that the development of a single IoT connectivity adapter could take 13 to 16 weeks and cost $40,000. This obviously poses a significant hindrance to growth, especially as ongoing software maintenance costs are typically 3 times the initial development cost. Other enterprises have chosen to go all in with one of the big cloud vendors, embedding their vendor's device agent or SDKs into the core software of their connected product and permanently tethering their fielded devices to the capabilities of that vendor. Whilst this does initially reduce some complexity, it also significantly limits strategic multi-sourcing, complicates deployments across regions with different data regulations, and excludes sales in B2B2X opportunities where the end customer's choice of cloud platform is sacrosanct. Now, there is a third option, with the open source ThinEdge.io initiative that provides robust, extensible, cloud-agnostic IoT connectivity. Through providing standardized cloud and inter-process connectivity, it simplifies software development and allows apps developed in different programming languages to be easily integrated within the same product. This reduces the number of code variants for hardware and IoT platform combinations and the associated software management overhead. Furthermore, with a growing ecosystem of community and commercial software being developed for the standard, enterprises can accelerate the time to market and efficiently increase the level of sophistication of their products. When considering connected products, it is beneficial to understand where they reside on the edge continuum of distributed compute resources, typically framed by near-cloud fog compute at one end and microcontroller-based micro edges at the other. Most IoT edge discussions today focus on the so-called thick edges deployed onto industrialized PCs with many gigabytes of RAM that allow it to support cloud-native technologies like virtualization and containers. The category used most in connected products, however, is thin edge with only megabytes of RAM and a lightweight OS. Thin edge dominates the embedded systems market, with the Linux variants like embedded Linux, Debian, and Angstrom being used in over 30% of all products. What is important to consider is that at this end of the continuum, the overall level of sophistication is low, but the volume of deployed edges is extremely high, which imposes a very stringent control of development and production to ensure conformance to the predetermined bill of materials. So last year saw IoT considered to be important to 50% of all embedded projects for the first time, which is a huge statement considering the heterogeneity of the projects. Of the IoT projects in progress, 55% of them are creating edge devices or systems through enhancing the capabilities of previously unconnected products and creating new natively connected products. However, with 44% of all embedded projects being new to the world, additional challenges are created in keeping costs down. The EE Times found that 58% of projects are completed after the scheduled completion date, regardless of the advances in development tooling and methodology. One potential reason is for the rising level of sophisticated demanded in products, evidenced by the 50% year-on-year increase in IoT to cloud projects being undertaken. IoT connectivity and analytics expertise are essential to these projects and have caused the first significant change in the average embedded product team for the last 5 years. With the other engineer category of non-typical embedded resources growing by 200%, whilst virtually every other category remained the same. In developing connected products, a number of common challenges need to be overcome. Networks can be unreliable, unsecure, and in some cases, expensive to use. Unfortunately, connected product manufacturers need to ensure that their data is transferred reliably over these unreliable networks. We recently worked with a company which has devices mounted on elevators. These elevators move up and down in the building. When they're at the top of the building, they have great cellular connection. And when they're in the basement, they have extremely poor connection. In this scenario, you can imagine how difficult it is to transfer a new software version to these devices. With the cellular networks, you can have additional challenges, like limited throughput in remote areas and the need to pay for every byte sent. Here, a lot of emphasis is put on reducing the messaging traffic, which can save a considerable amount of money when connecting hundreds of thousands of devices which are on 24/7. Once the device is connected, it can be managed remotely. With over-the-air firmware and software updates, this allows manufacturers to ensure that fielded devices are running the optimum software and enables new functionality or configurations to be distributed. As already mentioned, these connected products are built to a tight bill of materials, which is optimized to be as price efficient as possible at production scale, and often results in bespoke builds. Of course, there are already solutions out in the market that solve some of these problems, like the connectivity agents or SDKs from cloud or hardware vendors. However, these only support their specific platform, which imposes vendor lock-in that might be okay for some enterprises, but is not acceptable to most. It is for this purpose that we initiated the open source thinedge.io project with our lead contributors IFM, Nexus, Adamus, Initum, and a number of others. The project draws from our combined experiences connecting millions of IoT devices to the cloud. Many of these projects didn't start from a green field. Instead, the devices were already developed and running software. For example, PLC manufacturers wanting to connect their devices to the cloud to transfer operational data like real-time analytics results. Gateway partners wanted to optimize the configuration of industrial field bus converters when connecting to SCADA historians. And industrial machine manufacturers wanting to provide remote monitoring and management of their equipment to ensure optimum performance. In all of these cases, there is existing software to which thinedge.io can be installed to provide out-of-the-box cloud-agnostic connectivity and robust device management with a low compute footprint. This allows embedded device developers to separate the software development life cycles of their business logic from the connectivity logic and gain considerable efficiencies in the process. Let's have a look to see what's included in the thinedge.io project. Firstly, thinedge.io is available under the Apache 2.0 license, so you are free to make it part of your own connected product, deploy it on your own hardware, and run it to next-gen software. It is designed to run on resource-constrained devices, which could be powered by ARM v6, v7, v8, or other processors, with only a small amount of memory available. As mentioned earlier, this is a complete contrast to the thick-edge platforms which typically run cloud-native technologies. To connect to the different cloud platforms, thinedge.io uses the MQTT bridge that provides an MQTT client to connect to all these platforms. MQTT is probably now the most widely used IoT protocol and supported by all the cloud platforms stated here and most others. But why is it called an MQTT bridge and not MQTT client? This is because thinedge.io includes an additional MQTT broker component. Traditionally, devices are connected to cloud platforms using device SDKs, and each vendor had SDKs for different programming languages. Cumulocity IoT, for example, has device SDKs for C, Python, Java, and so on. And the same is true for Azure, AWS, and other vendors. We found that this language-specific approach has a lot of flaws and restricted us in supporting even more languages. So instead of compounding the problem with more language-specific SDKs, we decided on an approach where code written in any programming language can connect via an inter-process communication protocol. It was then obvious not to invent a new protocol, but to reuse the common MQTT protocol again. The MQTT broker provides the communication protocol between the different software components resident on the device. So now we have the inter-process and cloud communication protocol established, the data integration needs to be considered. For this, there is a data mapper. The data mapper adds semantics and reformats the lightweight internal data format so that it can be correctly recognized by the destination cloud platform. Each cloud platform typically requires its own data format, meaning that a temperature measurement captured on the device, for example, needs to be in the correct format to be recognized as a temperature measurement in the destination cloud platform. Protocol interoperability is needed, but also data format interoperability, and this is provided by the data mapper. The last component that connects to the MQTT broker is a device management agent. The device management agent provides all device management features designed for remote and over-the-air updates of firmware, software, and configuration. It is built to be extensible with plugin support for Mender, Debian, Docker, and more. In addition, it also provides monitoring of the components of the IoT device. Lastly, there is a command line interface. This allows easy configuration and starting and stopping of the complete thinedge.io. In our experience, we have found that it is non-trivial to manage certificates in IoT devices, especially for newcomers. So we have put a lot of effort into providing certificate management that makes it easy for both developers and also operators in live deployments. With the foundation technologies provided by thinedge.io, we are working with the contributors to make a range of third-party modules available on both a community and commercial basis. This further simplifies the development in creating sophisticated connected products. And as this is an open source project, we are open about our technology choices. We have developed most of the key components in Rust, including the command line interface. But we want to emphasize that anyone can contribute components in any programming language using our plugin mechanisms and their interface. As mentioned, we created a simplified MQTT payload format for the internal MQTT broker and various payload mappers for the different cloud platforms and services. These are all extensible, and you can use your own payload standards in combination with the corresponding mappers. So to summarize the advantages of thinedge.io, we have put a lot of effort in providing more options for you. We didn't want to reduce the number of alternatives, but increase them to your advantage. So you can connect to many IoT platforms out of the box. You can use any programming language, C, C++, Rust, or whatever you like, and send data to the cloud using the internal MQTT bus. As mentioned, internally we use Rust a lot because we found it to be a very secure language which is still very efficient. But you can use any language you're comfortable with. You can use any message payload, your own payload format, cloud-specific ones, industry-specific formats like Aqua, and so on. You can use any hardware or Linux-based operating system platform. ThinEdge.io comes with robust device management based on our combined experience of managing millions of globally deployed devices. It also includes an over-the-air software management agent that is extensible for different software artifacts beyond Debian and Docker. There's also firmware management, configuration management, and monitoring, with more capabilities during the coming releases. As ThinEdge.io has been created to run on devices with limited resources, we are targeting a resource usage less than 16 megabytes of RAM, and have put a lot of effort into ensuring its reliability with bootstraps and other mechanisms. So I invite you to get involved and find out more at our website, thin-edge.io, or our GitHub project page, and follow us on Twitter. In addition, I'd like to invite you to the first ThinEdge.io community meetup on the 27th of October. We are keen to engage with the embedded software engineers and software developers interested in ThinEdge.io, and aim to cover an overview of ThinEdge.io, technical deep dives into cloud connections, software management, and extensions. Also, contributor sessions on security, industrial protocol adapters, stream analytics, and more. Don't miss it. So lastly, thanks for listening. I really hope you can now see the advantages of leveraging an open source software project for secure cloud agnostic IoT connectivity. Please don't hesitate to contact me directly or check out our website, ThinEdge.io, and also our GitHub page. Thank you and stay safe.
Terrific stuff, Philip. Really enjoyed that, and was surprised to hear so much about the advantages of open source. I mean, obviously that's a discussion that's been around for a long time, and we've got, incidentally, plenty of time. So I wanted to start with a couple sort of open-ended questions for you. You know, the Apache group has been around for more than a decade. You know, there have been long discussions about the value of open source and how it works. And you did a great job of outlining the advantages. Are there any disadvantages to going with open source platforms and software? Or is the answer may be no, but I thought I'd ask.
So I think there was another open source project relatively recently that got to a stage where it's recognized by the industry IoT groups, the industry 4.0 groups, as being at a production ready stage. So typically with all kind of early open source projects need to be a certain level of maturity and stability, and that's what's been accelerated with the contributors we have. So Nexus is based on the whole business is based on security. IFM, the whole business is based on industrial instrumentation and connectivity. Atomos, the whole business is based around making machines. Intrum is a whole business is based on sort of solution engineering. We have a number of kind of PLC and gateway manufacturers kind of built into this space. So we're essentially hyper accelerating something to a good state, but also because we've selected just a sweet spot of capabilities that are required by the majority of use cases, the likelihood for that to get to a production ready state is extremely high in a short period of time.
Interesting. How can folks get involved in this open source project? You know, you mentioned the meetup coming up. Are there other avenues available? Yeah,
so there's a sort of growing dialogue on GitHub. So GitHub has an issues page. So please kind of scan through there to see what issues have been raised. Also, kind of raise queries. Some of those kind of issues could be requests to support us in ways that aren't necessarily code. So we have some contributors who are helping us with demos. Some contributors are helping us with kind of user experience, kind of involvement and feedback. So please use a GitHub as the first point of call. Or contact us on Twitter, but GitHub is the kind of first point of call. We regularly monitor that. So, I suppose outside of that, the first meetup will be the opportunity to sort of fully collaborate with a kind of a growing ecosystem of stakeholders involved in this.
Right. What are the next features on the roadmap, on the development roadmap? It sounds like there's a lot going on.
Yeah. So as I said, we're sort of focused on the specific capabilities required for cloud agnostic, secure IoT platform connectivity and robust device management. So there are additional features for that to allow improved health, remote access, and also support for additional software artifacts outside of Debian and Docker. So I think Snaps is mentioned on the architecture, and that's actually on the roadmap plan. It natively supports Azure IoT and also Cumulosity IoT. We're working with one of our contributors to build the AWS adapter in there. So these are all coming through. So and obviously what you need to recognize is that it's an open source project. It's community kind of built. So we don't necessarily have the same definitive roadmap as you would do from a commercial project, and but because of that, it's been driven by what the market needs.
Right, and you mentioned just now some of the platforms that are involved. It sounds like everybody's involved. Is there anybody not involved that's sort of a major player? I kind of can't think of one.
So we're actively speaking to most of the major players and all the contributors and sort of speakers on the session today. I mean, we'll welcome them into the fold as well. So once again, it's this is a open source community driven activity. So we can only get to the result that the market's demanding if we actually contribute and work together. So so we're looking for all contributions for all avenues to kind of speed up development.
Right. Hey, you made one comment in your presentation that I thought was really interesting, and I was wondering if I could get you to expand on it. And that is separating the business logic from the connectivity logic. Could you talk to us about that a little bit? I mean, why is that important? How does it work?
So what we've found is in a number of projects, specifically with industrial machine manufacturers, they need to maintain a high level of separation between the different components they have. So kind of separation on hardware, separation on cloud platform, but also as the sort of connectivity component is heavily related to the cloud platform, then if they have business logic that looks at kind of the performance metrics of an air compressor, as I mentioned. To date, there's been a high need to actually have kind of almost different versions of that code or that firmware that would actually have multiple cloud vendors. They need to manage that. And once again, by separating the business logic, so the compute angles that do the analytics, create the KPIs, do the kind of high frequency data analysis, from those that manage the connectivity back to your platforms, then you can actually build the best of both and actually then be able to deploy them onto any hardware platform that would actually support that level of capability. So, and that's, I suppose it's almost kind of a software development 101, isn't it? Actually, you modularize and sort of compartmentalize things. And then that means you have so 2 bits of software you need to manage as opposed to 1 bit of software you need to manage for each combination of IoT platform and hardware.
Right. I got a question over the transom that I think perhaps refers back to some of the discussion we were having about platforms, but the question is a bit cryptic. Including graphical programming languages, does that ring any bells for you?
Yeah, so the classic one here is Node-RED, isn't it? So I think maybe not a lot of production ready, but a lot of prototypes in the embedded space are developed using Node-RED. So it's free, it's open source, and now it's kind of considered to be production ready. So if you with Node-RED, a lot of times you'd have to create multiple flows or segments of flows to connect to different platforms. Whereas what we've found from our experience, and obviously with our contributors' experience, is that if you have, well, using Node-RED, and I think there's an example already on YouTube, all you need to do with the Node-RED flow is actually send the data to a local the local MQTT broker before it's sent out. And then you can actually then set a configuration up to say, okay, yes, send it to Azure, yes, send it to Azure and Cumulocity IoT, send Azure, Cumulocity IoT, and AWS, or Deutsche Telekom, Cloud Dinga. So it simplifies that as well. And as always with software development, so what we're starting to have in the IoT space is a evolving need to manage software components in the same way they've been managed efficiently in a structured way in the IT space. So you have specific tooling that looks at enterprise architecture evolution and management. And at some point in time, that will naturally come across to the IoT space because we have so many different software modules deployed into so many different assets, we need to manage in the same space. So if there's any way to reduce the number of software modules that we need to manage, that's generally better and more cost effective than having multiple versions out in the field. Right.
Right. Terrific. Hey, you can always tell the questions that are coming from me, Philip, because they tend to be lower level. I've got another one, and that is, we talk a lot about over-the-air provisioning, and you mentioned OTA for updates of firmware and software, and you mentioned it in the context of sort of managing licenses, et cetera. Can you talk to us a bit more about that? Do your less experienced users understand the importance of it?
So obviously, as I was speaking from a thin-edge.io community point of view, I suppose that I think one of the panelists before mentioned there's a large difference between your, let's say your early IoT company and your more mature IoT company who's actually got the scratches and the bruises, etc., from going through many different cul-de-sacs. Obviously, for the latter type, they have they've got a number of devices out in the field, and maybe hundreds of thousands, and they know, they know that managing software is essential because there's issues they need to resolve. The example about the lift manufacturer, I mean, they're bound by local regulations to ensure the level of connectivity, the support, the maintenance, the local fire safety regulations, etc. Plus, also you have the requirement to update software to cope with, security attacks, etc., etc. That's a natural need, but they've gone through all those hurdles to start with. I think for the let's say the less mature organizations, I think they're a lot more savvy of the need now than they were, let's say, a decade ago. Right. Partly because there's more case studies of these larger companies. So if a larger company talks about the bruises it suffered, then typically the smaller company starts to listen. But there is this what do you call it? Kind of a pivot point, let's say, where it's kind of moving from a prototype to a POC or a pilot. And I think one of the panelists mentions it as well. So you kind of go from a kind of DIY homegrown product, then you try to work out, okay, how do we scale it? And there's a factor you need to move there. So typically, let's say your POC has been based on business logic, and then your pilot or first deployment is actually then also based on operational logic, which device management is a key part of that.
Right. No, terrific stuff, and appreciate your perspective. I'm sure there's a lot of people there that could benefit from it. Philip Hooker, Vice President of Strategic Programs and Cloud Innovation with Software AG. Hey, Phil, thanks so much. Really appreciate it. Enjoyed it, and I'm sure our audience did as well.